So you've seen the periodic table, and every time you see the periodic table, it's shaped like that. Okay? Fact is, if you want to prove to alien intelligence that you know that how the world works, if you show them that shape, they would say, wow, they know chemistry. Because their periodic table is going to be the same as ours. We got the same elements. The elements are going to behave the same way. They're going to see the same patterns we did. So periodic table is the same. So how did they come up with it? And why is it the way it is? That's going to be the first part. How did they come up with the periodic table? Why is it the way it is? The next part will be about what patterns can we see on the periodic table that will help us predict how chemicals react. Because that's ultimately our goal is, if I mix this chemical and this chemical, what's going to happen? And we now know enough about the atom that we can talk about what's going to happen when you put two chemicals together. That's where we got to. That's why we took a month and a half about the atom, because we need to know that much about it. Okay. So, history. Okay. So, scientists are pattern seekers. They look for patterns in behavior. And that pattern turns into a law. And that law, you try to explain with a theory. So first you got to notice the pattern. So one of the first people to notice the pattern was a German named Dobereiner. And he found that there were elements that he could group into triads. So, triad. What's a triad going to be? It'd be three things, right? And what gave them those was they behaved the same way. One of his triads would have been lithium, sodium, and potassium. He would have noticed that if you put lithium, sodium, potassium in water, they react violently. Hey, those belong together. Okay? So you would take chemicals like those three. And then they were similar in this way, but they were different in other ways. He looked at how they were different. He measured stuff about their differences. So he measured things like density, the amount of reactivity, the melting point. Okay? He found that the properties followed a pattern. That if he looked at his triad, no matter what other thing he looked at, the same one was in the middle. Between lithium, sodium, potassium, lithium has the highest melting point, potassium has the lowest melting point, sodium's in the middle. Between lithium, potassium, and sodium, lithium has the lowest density, potassium has the highest density, sodium's in the middle. That kind of stuff. You look at melting point. Lithium's got the highest melting point, potassium has the lowest melting point, sodium's in the middle. So there's got to be some reason that the same one's in the middle. There's trends that go both directions, but the same one's in the middle every time. So there's got to be an underlying reason. But he ran into some problems. First of all, he couldn't find triads for everything. And then they found rubidium, which was the fourth thing that behaved like sodium, potassium, and lithium. How can you have a triad if you got four things? The expanded triad. Okay, so why couldn't he get any better? Why didn't the triads work out? The triads didn't work out because it's not threes. And what his limitation was this was 1829. they just decided, they just started changing the definition of elements, right? So we're 50 years past Dalton. Our definition of elements now is what you tear apart. And they didn't know that many elements. You don't have enough pieces, it's hard to see the pattern. So they had to wait until more pieces were discovered, more elements, more different kinds of atoms before they could actually notice what the patterns were. Okay. The next one that comes up on the list is Dmitry Mendeleev. Mid-1850s, during the rule of Peter the Great. Okay? And Peter the Great decided that Russia, which was a poor agricultural country, was going to join Europe. And Moscow was going to be just like a European city, and they needed educated people, so they started a university in Moscow. Dmitry Mendeleev taught chemistry there. Well, if you're the first person to teach a chemistry class in Russian, you have to write the textbook. Okay? And in the 1850s, they didn't know much about atoms, just how much they weighed, which was the lightest atom, which was the heaviest atom. That's all they knew. Okay? So what you studied when you studied chemistry was you memorized how chemicals were going to react. Because nobody knew why they reacted that way. The only way to do it was to memorize it. So that's what Mendeleev was trying to do. He was trying to make a table that made it easy for his students to memorize how things behave. That's what he was trying to do. Okay? Okay? So he had more information than Dobereiner. He had more information than Dobereiner because they had discovered more elements. And they'd actually put them in order, they had figured out which were the lightest ones and which were the heaviest ones. So, he just, to make his list, he had to find an organizing principle. And alphabetical order doesn't work. Right? So, his organizing principle was lightest element, heaviest element. Okay? And when he did that, he saw a pattern that Dobereiner didn't see. He saw that there was repeating properties, but it didn't have to do with triads. It was just every so often they repeated. Okay? So he said lithium reacted with water. And then 7 elements later, sodium reacted with water. So lithium reacted with water, then sodium reacted with water. So those two are similar. Okay? Lithium combined with 1 hydrogen. Sodium combined with 1 hydrogen. The element after lithium, beryllium, combined with 2 hydrogens. The element after sodium, magnesium, combined with 2 hydrogens. So the one after it behaved like the one after it. So there was a repeating pattern of properties. Okay? He said, oh, this will make it easy for my students to learn the properties. I will just put them in columns by similar properties. Teachers. They're having too much fun. Okay. So, columns by similar properties in order of increasing atomic mass. You notice the pattern. Okay. Now, He ran into a couple of problems. His system didn't work perfectly. There were some inconsistencies. What do we mean by inconsistencies? Well, if you put them in order by weight, iodine is 126.9 and tellurium is 127.8. I just got the numbers off the periodic table. So if you put them in order by weight, iodine comes before tellurium. But the elements above them, bromine and selenium, iodine behaved like bromine, tellurium behaved like selenium. They were backwards. Those two elements were backwards. That's a problem. It's a problem he had to decide which is more important, that I keep them in order by mass or that I keep them in the right columns. And he said, I don't know the reason for anything, but it seems to me there's got to be an underlying reason why they behave the same way. I should put them in the same column and get them out of numerical order. Okay? So he got them out of numerical order, but lined up the properties. He also found some gaps. He could find that aluminum and boron behave the same, and that carbon and silicon behave the same, and that phosphorus and arsenic behave the same. But he couldn't find anything that was lighter than arsenic that behaved like silicon. He couldn't find anything lighter than aluminum that behaved like aluminum. Or lighter than arsenic that behaved like aluminum. Okay? So he said, whoa, we must have some elements we haven't discovered yet. The reason why there's gaps on his tables is because nobody had found those yet. But he just didn't say they were undiscovered elements. He would say, and when you find them, this is what they're going to be like. Because he could predict their behavior before they were found. In fact, predicting their behavior made it easier to find them. You knew where to look. You knew what to look for. Now, your book doesn't mention this. And it's an important point to me that they don't mention it. At the exact same time that Mendeleev was making his table in Russian in Moscow, a guy named Lothar Meyer was making the exact same table in Berlin. They both made the same table at the same time. It's proved that they had no correspondence with each other. They didn't visit each other. They both came up with the same idea. But your book does not mention Lothar Meyer. Why? Well, Lothar Meyer was a German chemistry teacher, and he was giving his students a table to help them learn chemistry. Mendeleev said, no, this is not a table for helping memorize stuff. There are underlying reasons for this, and these properties are going to repeat. Okay? And I can use that repetition to predict things you haven't seen. So a couple years later, a Frenchman named Lecoq discovered a new element. Okay? He called it gallium after the Latin word Gaul, which was the Latin name for France. And he published that he had discovered this new element. He had isolated this new soft silvery metal. And Mendeleev read his paper and wrote him a letter, said, I knew that there was an element that would weigh about that, but you've got the density wrong. Now, Mendeleev had never seen gallium. Fact is, the only person who'd ever really seen it was Lothar Meyer. Or no, Lecoq. Lecoq was the only person who'd really seen it. So how come Mendeleev could write Lecoq and say he got the wrong density? Well, Lecoq says, you got to be wrong. I'm the only person who's ever seen it. I'm the only one who could ever have measured it. How can you tell me I'm wrong? Well, he measured it again, found out Mendeleev was right. And that's why Mendeleev gets credit and Meyer doesn't. Meyer, it was a tool that you memorized to memorize how chemicals reacted. It wasn't about how chemicals were. It's just a tool for memorizing, like a multiplication table. Okay? Mendeleev said, no, there are reasons behind this. There's something going on and it's important. And that's why he gets credit with the periodic table and the periodic law, that if you put them in order of increasing mass, their properties repeat, which is how we draw a periodic table. Makes sense? Why we get y of that. So, how did Mendeleev organize this table? Okay. Which one are you? No sense. This is a question. What's the answer? Wow. Copying mindlessly. Check to see if you got. Which one? What did he do? Did he group elements by properties, look for gaps? Did he put them in order by mass, then put the ones with similar properties together? Did he rearrange them in order to keep the mass in order? Did he multiply Doe-Breiner's triads to make them bigger? Which one of those did Mendeleev do? Which one? B? Yeah. You can't know ahead of time that you're going to look for gaps, right? He didn't know there were going to be gaps until he made the list. Hey, you put them in order by mass, and then group the ones together with similar properties. That's what Mendeleev did. So that's Mendeleev's table, 1800. Our table is different because we know more elements than Mendeleev did. We're up to 120 now, which is about twice as many as he knew. Hey, the modern table, one you use all the time. It still has elements grouped by properties. And how are they grouped? What do we do with the properties to group them together? Where do we put the ones with the same properties? In the same column. Hey. But instead of being an atomic mass order, now it's an atomic number order. And when you put it in an atomic number order, all of Mendeleev's problems go away. He had a problem he didn't know about because there was no way for him to know. His table was missing an entire column of elements. And that's got to do with how they found elements. Since an element was the simplest piece of matter, what you did was you found something that you didn't know what it was made of, and you put heat or electricity through it to tear it apart into pieces. If you knew what the pieces were, they were uninteresting. and you threw them away. Because you're looking for what you don't know. So the parts you don't know what it is, you try to tear it apart. If you can tear it apart, if you know what the pieces are, whatever piece you know, throw away, it's unimportant. When you don't know, you try to tear it apart again. Eventually you'll reach a part where you can't tear it apart anymore. And that's when you have an element, because you can't tear it apart anymore because it's all one kind of atom. You have only one kind of atom, no matter what you do to it, you're only going to have, you can't make it any smaller. You can only change it by adding things to it. Does that make sense? Well, the ones they hadn't found, you're not going to find this way. Okay. So here's why they found the column that he didn't know. It has to do with refrigeration. It had to get good enough refrigeration. Late 1800s, early 1900s, they finally had a good enough ways to make stuff cold. Because what happens if you take air and you cool it, the first thing that happens is all the moisture comes out. Condensation, dew, right? If you keep cooling that air, the next thing that comes out is solid carbon dioxide, dry ice. You got to get down to about negative 70 Celsius before that happens. If you keep cooling it and get down to about negative 150 Celsius, the oxygen in the air will turn into a liquid. Okay? And if you keep cooling what's left, when you get down to negative 170, the nitrogen will turn into a liquid. And that's about all they thought was in air. But when they did that, there was still a little bubble of gas. And when they heated this gas up, it glowed. And when it glowed, it made lines they'd never seen before. They've discovered a new element. That element is argon. Argon makes up about 0.5% of our atmosphere. You're breathing argon right now. Okay? Why hadn't they found it? Well, argon is a noble gas. The reason why they're called noble gases is because they don't mix with the common elements. They're called noble gases because they don't react with anything. So you're not going to find them in a compound because they don't react with anything. You're not going to find it by tearing stuff apart because they're not ever together with anything. Now, once you find argon, and you know it's in between the weight of chlorine and potassium, you now know that you're missing a column. And you start looking for the other ones in that column. And that's when they realized that helium's light from the sun, they could find it here on Earth as alpha particles that they captured. Okay. So once you find one, you fill the rest in. Okay. So here's what our table looks like. You got to use vocabulary to describe parts of it. So horizontal rows are periods. Horizontal, flat. There are 7 periods. And they're not named, they're just numbered. 1 through 7. So you can either say period 3, or you can say 4th period. Either way is okay. It's either in period 3 or it's in the 3rd period. It's in row 3 or it's in the 3rd row. Yeah, those would be the same thing. The vertical columns are called groups. A vertical column is a little bit redundant because columns are always vertical once they're installed. And how do they get into those groups? Well, what did Mendeleev group them by? Similar properties. So things in the same column behave the same way. Not identical, similar. And because they're similar but not identical, there's a second term they sometimes use instead of group, and that is family. Now, if you look at the top of your periodic table, it's got a set of numbers. It's got a couple sets of numbers. One of them is 1 through 18, and then the other one is 1A, 2A, 3B, 3A, 4A, 5A. Okay, notice where the B's are at and where the A's are at. The A's are in the tall columns. The B is this middle section. Right? The ones in the tall columns, they're called representative elements. Or sometimes main group elements, depending on the book, but representative elements. They're called representative elements because all the patterns we're going to talk about work really well in these. The patterns are well represented. That's why they call them representative, because the trends work, the patterns work. Things a little bit iffier here because different electrons are doing different things. So we're going to use the ones that are 1A, 2A, 3A, 4A, 5A. And we're not going to use the 1 through 18. So just to make sure everybody's got a good grasp of where periods and groups are, what would the symbol of the element in period 3, group 4A? So period 3, group 4A, 1, 2, 3, 4A. So, okay, now, I don't want you to be misled. These are the ones we want to use. Your book also includes the 1 through 18. My periodic table, I don't know if you can tell, I had to change it. It was done a third way, with Roman numerals and letters. Okay, 3 different ways. Is that efficient? So there's a group of people who fixes this stuff, okay? And they are called the International Union of Pure and Applied Chemistry. They're the people who set the rules. So we're all doing stuff the same way. Okay? So the reason why there's 3 sets is because 2 different people were doing it. The stuff that was that was the US and Western Europe. The Roman numerals, that was the Soviet Union and Eastern Europe. This was a remnant of the Cold War. East versus West, democracy versus communism. Okay? So, it's not good to have 2 periodic tables out there. So the East and the West came together at the Union of Pure and Applied Chemistry and said, oh, we need to settle on one of these. And the West argued for theirs, and the East argued for theirs. And there's good reasons for both of them. There's reasoning behind the numbers and the letters, and that it's really good reasoning. But there's not a good reason to choose one over the other. And since these people didn't want to get caught in the middle of something, they punted. and said, the official way will be to number them from 1 to 18. So the official one is numbering from 1 to 18, but it's not the one we're going to use because you lose information by numbering from 1 to 18. So we're going to use the Arabic ones with the A's and B's. Now, every periodic table I've ever seen has got a zigzag line going through there. I don't know if you noticed, it's always there. What that zigzag line does is it breaks the periodic table into 3 categories. Things on the left-hand side of the zigzag line, not touching the zigzag line, are metals. Okay, now there's one exception, that's this one right here. It touches the line, but it's a metal, because that's aluminum. And if somebody asked you what aluminum was, what's one word you would use to describe it? About metal. Everybody agree that aluminum's metal? So do chemists. Okay? So everything on the left-hand side of the zigzag line, not touching the zigzag line, is a metal. What does it mean to be a metal? Well, metals are shiny. They have a shiny luster. Guys think that's true? So if it looks dull, you probably got rust on the outside. Cut a fresh hole, you'll see it shiny. Then they use some specific words. Ductile. And if you look up ductile or any place you look it up, this is what they're going to, this is how they're going to define it. That it can be drawn into wires. We're not talking about art here. We're using the word drawn the way they used it when they said drawn and quartered. Okay, drawn means to pull tightly, pull hard. So drawn and quartered was they would tie a rope to each of the person's limbs in the town square, and then tie the other end of the rope to a horse and send the horses in 4 different directions. That's what drawn and quartered was. You pulled into 4 pieces. Okay? Drawn means pulled really hard. So what to say, if you pull a metal really hard, it'll get thin in the middle, thin enough to be a wire, like taffy. Taffy is ductile. You grab it, you pull it, it gets skinny in the middle first. Metal does that, you just have to pull a lot harder. And what it looks like to us in our everyday life is that metals stretch before they break. They stretch and get skinny before you can tear them apart. That's what ductile looks like. They stretch, and if you pull just right, you can pull it just right, and you can pull it into a wire. Okay? That's how they make wire. They pull metal. Okay? Metals are malleable. When I see the word malleable, the first letters remind me of mallet. A mallet's a hammer. And if you look up malleable anywhere, it's going to be hammered into thin sheets. They picked gold because gold was the most malleable. When they wanted gold foil, they were trying to get it as thin as possible. They picked gold because gold could be made thinnest. But you can make it thinner and thinner, so it's only a few atoms thick. It's one of the most malleable metals. What malleable looks like us, we don't go around hitting things with hammers. What malleable looks like to us is that metals dent before they break. Or they bend before they break. Has that been your experience? That it bends before it breaks? Okay. Metals are good conductors of heat and electricity. That means they let heat and electricity move through them easily. Fact is, on our periodic table, We talked about all the A's. Well, here's where all the B's are. And the B's are transition metals or transition elements, depending on who you talk to. Well, they're transition elements, but they're all metals because they're all on the left-hand side of the zigzag line, not touching the zigzag line. On the right-hand side of the zigzag line are the things that aren't metals. Those are called non-metals. Let's go with the obvious one. So on the right-hand side, not touching the zigzag line, are non-metals. What are they going to be like? Not like metals. So instead of shiny, they're dull. The opposite of both malleable and ductile is one word: brittle. Brittle means it doesn't stretch, it breaks. And the opposite of a conductor, sometimes I write non-conductor, but the real name for it is an insulator. I mean, think about it. If you don't want heat to go out the walls of your house, what do you put in the walls? Insulation, right? What's the plastic on the outside of wires called? Insulation, to keep it from conducting to you. And the ones touching the zigzag line are called metalloids or semi-metals, depending on who you talk to. And I wrote properties of both. It's really in between. They're kind of shiny. They bend a little bit, but then they snap. But most importantly is they're sort of conductors. They're semiconductors. The most commonly used of those semi-metals is this one, right there. That's silicon we talked about. There's a whole area up in Northern California called Silicon Valley. It's not really a Silicon Valley. It's where they build computers, because computer chips are made out of silicon. Why? Well, all a computer is millions of little switches that are either opened or closed, right? Either conduct electricity or don't conduct electricity. That's all a computer is. Now, if you made the switches out of metal, it would always conduct, because metals always conduct. If you made it out of a non-metal, it would never conduct. But you make it out of a semiconductor, a metalloid, you can control when it conducts and when it doesn't conduct. So it sort of conducts, and you can make it so it will and make it so it won't, so now you have a switch. Turn the electricity on and off. It doesn't conduct as well as metal, so you got to sort of force the electricity through. That's why computers get hot. It's because they don't conduct really well, but you can make them conduct. So the heat you feel coming off the computer is because the electrons are forcing their way through, because they don't conduct really well. So they take a piece of silicon, and they actually use other semi-metals. They put in some germanium and some arsenic. Those two right there, and that makes the switch. Use those three semi-metals to make a switch. Hey, homework's out of the book. Have a pleasant day.